Hi everyone, this is your first video of your organic analysis topic. Organic analysis is all about identifying organic substances using a range of techniques. So you're going to have a little look at a couple of techniques, mass spectrometry and infrared spectroscopy, and then you're also going to look at percentage by mass and having a little look at some chemical tests that you can do for different functional groups. So for this first video in the series, I'm going to talk about something that you should already know about, which is mass spectrometry. I'm going to just recap everything that you did when you first saw it at the start of physical chemistry. So you'll need your class exercise book in front of you, pens and highlighters and whatever you like that you would normally use during a lesson. And I'd just like you to watch through this tutorial and make your notes as you would in class, and then those notes can come to class with you next time I see you. So first of all, something to be wary of. If you are revising, if you're researching at home, you're looking up on the internet or in old textbooks, you might see a different type of mass spectrometry than the one that you should have learnt about at the start of the year. So if you come across this type of mass spectrometry, a diagram where the tube that the particles travel through goes through a bend, and it uses an electromagnet and it has a deflection zone, then you are definitely looking at the wrong type of mass spectrometry. This type of mass spec was from the old specification for AQA and for other exam boards, but we're not looking at that anymore. They've changed it now to what's known as time of flight mass spectrometry, which is this one on the right. So if you're going to look, further reading or anything else that you want to have a little look at to look into it in more detail, you need to make sure that you are finding this type of mass spec and certainly not this one. Okay, so now that we're looking at the correct technique, there are a few different stages in the mass spectrometry process, so I'm going to talk you through each of the steps in the process. You can make your notes, and then we'll have a look at a couple of exam-style questions. So, first things first, the sample has to be put into the mass spectrometer. So usually it's vaporised, and then it enters the mass spec. It's important to notice that it is carried out in a vacuum because we're looking at particles travelling through this and kind of measuring how long it takes them to get through this tube. So we don't want them hitting into any other particles, like air particles or anything like that. So we make sure it's done in a vacuum. So once inside the mass spec, we have the ionisation area. So the particles of your sample, your unknown sample, are ionised, usually to a +1 ion, and then they travel into the acceleration zone, which is here. After that, they approach what we call a field-free region or a drift zone, and they drift along this part of the mass spectrometry tube until they hit a detector. So first of all, we're going to have a little look at the ionisation in a little bit more detail. So there are two types of ionisation that they can ask you about, that you need to know about. This is the first type, probably a little bit easier to understand what's going on and easier to describe if you're asked to, if you've got a choice. So this is electron impact ionisation, also sometimes called electron bombardment. And this is one way of making the sample particles have a +1 charge. Ideally a +1 charge anyway. So how it works, we've got a filament, a very hot filament, which we also sometimes call an electron gun. And this electron gun fires really high energy electrons into the sample. And that's a really useful phrase as well for if you're answering any exam questions, you'll want to mention high energy electrons. So these incoming electrons from the electron gun smash into the particles of your sample, and they knock an electron out of the particles in the sample. So if we call your sample M, for example, for molecule, an electron comes in, hits M, and M becomes M+, and there's the electron that's been knocked out of the sample molecule. So it is M+ that travels through the rest of the mass spectrometer and gets detected at the end. Now this is your second type of ionisation, second method of producing the 1+ ions. And this type of ionisation is called electrospray ionisation. So this diagram is taken from AQA, so it should show exactly how the exam board want you to understand the process. So this one's a little bit more complicated, but what happens is your sample, before it's put into the ionisation area, is dissolved in a polar volatile solvent. So those words there, polar volatile solvent, if you're talking about electrospray ionisation in an exam, you'll want to use those words. They'll probably get you a mark. So the sample's then put into a hypodermic needle or a syringe, a capillary, very, very narrow, and it's pushed through at high pressure. Now, the tip of the needle is attached to a very high voltage, which you'll also want to mention in your exam. Now, as the sample's sprayed out, it becomes a fine mist. It's sprayed out and the solvent evaporates and your sample picks up a proton. So the sample, if we call it M, pen would help. If we call your sample M again, rather than M losing an electron, M picks up a proton, or H+, which is obviously just a proton, and becomes the MH+ ion. Now it's quite important to note the hydrogen there. Hydrogen has a mass, hydrogen weighs 1. So when your MH+ ion goes through the rest of the mass spectrometer and is detected at the end, it will be 1 heavier than the sample that you put in. So you need to bear that in mind. You need to subtract 1 from the molecular mass you get from your mass spectrum to find out what the sample was that you put in the first place. And that's only for electrospray. If you used electron bombardment, then your molecular ion peak weighs the same as your sample did, so it's not a problem. And now there's a bit of another warning for you. If you use this textbook, the CGP A-Level Year 1 and AS Chemistry for AQA, which most of you do if you're in my class, the electrospray ionisation definition and description is incorrect. So you'll see that it says in there, causing the particles to lose an electron, and the particles do not lose an electron. They gain a proton, and they become MH+, as we've just said. So be really careful with your textbook. There's an error in there, and you need to make sure that you're not writing that in an exam. This phrase here is absolutely fine if you're talking about electron bombardment, but not when you're talking about electrospray. And on that note, the electron bombardment's also missing from this textbook, but it is still relevant. Right, so back to the stages. We've put the sample in. We have ionised it, usually to +1. I'm just going to mention now that although we usually get a +1 ion, and we want a +1 ion to go through the rest of the mass spectrometer, you need to be aware that you can also get a +2 ion. So if you're using electron bombardment, for example, and the high energy electrons that are hitting the sample, they could knock 2 electrons out of your sample particles, and then they would become a +2 ion, and that's going to affect your reading of your mass spectrum later on. This is not very, this doesn't happen very frequently. So once the particles have been ionised, we're now looking at the acceleration area. It's fairly straightforward. So in the acceleration area, you've obviously now got positively charged ions travelling through that zone. So this stage involves an electric field. We've got positively charged grid here, which will repel your positive ion travelling that way, and we have a negatively charged grid here, which is going to attract it, so it will accelerate through that area. So electric field attracted towards negatively charged plates, something like that is what you want to write in your exam. Now, something that's quite important in this acceleration area, the particles that are travelling through here are all accelerated to provide them with the same kinetic energy. So you're probably familiar with this equation for kinetic energy. So kinetic energy is equal to half times the mass times the velocity squared. And as I've just said, the particles inside the mass spectrometer are accelerated to provide them with the same kinetic energy. And this is so that once they go into the next region, which is the drift zone, this bit here, sometimes call it the drift zone or the field-free region, where there are no fields to affect the movement of the particles, no magnetic fields, no electric fields or anything like that. Once all the particles have the same kinetic energy, we've just got mass and velocity left in this equation because kinetic energy becomes constant for all of the particles. So that means that the velocity, the speed at which they travel along this region of the mass spectrometer, is affected purely by mass. So velocity is proportional to the mass of the particle it's travelling through the mass spectrometer. Now, there have been some questions recently from AQA where you've had to use this equation to calculate all sorts of things. So the mass of the particle, the velocity of the particle, the sometimes the length of the tube, using the speed, distance and time equation and this equation joined together. So you need to be familiar with this, what it actually means. It usually gives you the equation with the definitions of the terms. So m is for mass, v is for velocity and so on. But you just need to be prepared for it so that it doesn't kind of catch you off guard. And I'm going to show you an example of one of those types of questions now. Okay, so here's an exam style question. Calculate the mass in kilograms of a single 59 cobalt plus ion. Assume that the mass of a 59 cobalt plus ion is the same as that of a 59 cobalt atom. So obviously the cobalt plus has just lost an electron, which doesn't really weigh very much anyway. So then you're given the Avogadro constant, which is a big clue as to what you're supposed to do. In fact, I'm going to change that slightly. That was looking like 6.022 times 1023, so times 10 to the 23 per mole. Then in the second part of the question, in a time of flight mass spectrometer, the kinetic energy of a 59 cobalt plus ion was 1.182 times 10 to the minus 13 joules. Calculate the velocity of the ion using the equation. And it would give you this equation, which is obviously the one we've just seen. Kinetic energy equals half mv squared. And it outlines that the m is mass in kilograms and the v is velocity in meters per second. Now, compared to some questions, I actually think this is fairly nice. I have seen some questions that have just gone straight in for this, assuming that you will know you need to calculate the mass of the cobalt plus ion. So to have it broken down is quite nice. It means that if you get part way through, you've obviously got these marks. And if you couldn't have done the full equation, at least you could probably do the first part. So if you'd like to have a go at this question before I show you how to do it, by all means pause the video, have a little go at it. It's only going to help you to practice, and then you can see if what you're doing is correct when you resume the video. So, using Avogadro to calculate the mass of a single ion. Well, we know the mass of the cobalt plus ion, or the relative atomic mass, is 59. So that means that 1 mole of cobalt 59 plus ions weighs 59 grams. We also know from the Avogadro constant that 1 mole of cobalt plus is actually 6.022 times 10 to the 23 cobalt plus ions, and that weighs 59 grams. So we want to know, instead of 6.022 times 10 to the 23 cobalt plus ions, we want to know, what about 1 cobalt plus ion? What does that weigh? Well, to calculate that, you just need to do 59 divided by Avogadro constant, 6.022 times 10 to the 23, and your answer should be 9.80 times 10 to the minus 23, and remember that's in grams. If you just go back to the question, it did ask you to calculate the mass in kilograms because the mass down here needs to be in kilograms. So take that answer, 9.80 times 10 to the minus 23, divide by 1,000 to get it into kilograms. Answer is 9.80 times 10 to the minus 26 now, kilograms, and that's your answer for the first part. Okay, so on to the second part of the question. In a time of flight mass spectrometer, the kinetic energy of a 59 cobalt plus ion was 1.182 times 10 to the minus 13, so that is your kinetic energy. Calculate the velocity, so that's the one we want to know, using the ion, and we've got the mass, so there's the mass that we calculated earlier. So now it's just a case of rearranging the equation so that you're not trying to calculate kinetic energy, you're trying to calculate mass, and then plugging in some numbers. So hopefully you're all fairly competent and confident with rearranging equations, but I'll show you how to do it anyway. So we've now got kinetic energy equals, we want velocity equals, so I'm going to start moving stuff from the right hand side of this equation, because we want the velocity on its own. So if we move this, and we remove this, we've got v equals, and all of these things need to move over to the other side. So first of all, we're going to deal with this half, move this over. So if we're timesing by a half, well, obviously we're dividing this by 2 by timesing it by a half. So on the right hand side, we're dividing mv squared by 2 currently. We need to get rid of this part anyway. So to get rid of the half, or the divide by 2 on the right hand side, we're going to do the opposite to the whole equation, so we're going to multiply through by 2. So on the left hand side, timesing by 2, we've now got 2 lots of kinetic energy, equals, well, on the right hand side, we're dividing mass and velocity squared, that term there, we're dividing that by 2. So now when we times by 2, that disappears, so we've now got mv squared. Your next part is to get rid of the mass. So we've got mass on the right hand side, we're multiplying by mass, so if we divide through the whole equation by mass, we can remove that on the right hand side. So we've got 2 kinetic energies, we're now going to divide both sides by mass, so we divide that by mass, equals, well, if we divide the right hand side by mass, we actually lose, because mass divided by mass, you get rid of it, it's just 1. So we end up with just the velocity squared on the right hand side. And now we're nearly there, we want v equals, but we've currently got v squared equals, so we're going to do the opposite to get rid of the squared. Opposite of squared is to square root, so we're going to square root the left hand side. 2 times the kinetic energy divided by mass equals, when you square root the right hand side, you're going to get rid of that squared sign there, so just v on its own. So now that we've got the equation looking like we can actually use it to calculate velocity, we just need to plug in some figures. So the velocity is equal to the square root of 2 lots of the kinetic energy. Kinetic energy we were given in the question there, which is 1.182 times 10 to the power of, minus 13. So we square root that, divided by m, which is the mass, which we calculated in the first part to be 9.80 times 10 to the minus 26. So if we plug that into the calculator, that gives us the velocity is equal to the square root of 2.41 times 10 to the 12, square root that, and we get that the velocity is equal to 1553140, which is obviously going to look a little bit nicer in standard form. So that gives us velocity is equal to 1.55 times 10 to the power of 6 meters per second. So that is the speed, or the velocity at which the cobalt plus ion is travelling through the mass spectrometer, or at least through the field-free drift zone. So we know that the particles, after being accelerated, all have the same kinetic energy, so they travel across the drift zone, and we know that the velocity at which they travel is dependent on their mass. So it's really important to know and really important to describe if you're explaining how mass spectrometry works in your exam, that the lighter ions travel faster because they've got a smaller mass, so they have a higher velocity through the drift zone or the field-free region, and the heavier ions have a larger mass and therefore a lower velocity, so they travel slower through the field-free region. That means that the lighter ions will hit the detector first, the heavier ions will come later. So that's where the time of flight is measured. We measure the time taken for the particles to leave the acceleration zone and to arrive at the detector. Then we can, the computer that's attached to the mass spectrometer will then use the kinetic energy equals half mv squared to work backwards, knowing the kinetic energy that the particles have got, knowing how long it took the particles to travel across this area here, and therefore working out what the mass of the particles is. And that's how we identify what was in the original sample. So the particles arrive at the detector. They've got a 1+ charge that they were given when they were ionised at the beginning, and when they hit the detector, the ions gain an electron to become neutral again. Now when they do that, they induce a current at the detector, and that current, the size of the current is dependent on how many ions are hitting the detector at the same time. Now, if you remember, ions that are hitting at the same time must be the same type of ion because they have the same mass. So the size of the current is put onto the mass spectrum as a bar, like these ones here. And the height of the bar represents the size of the current, which represents the abundance of those ions in that sample. So the taller the bar, the higher the abundance. That means the more ions were in there and were hitting the detector at the same time. So looking a bit more closely at the spectrum that's produced, here we can see the most abundant ion in this spectrum weighs 43, because that's the tallest, it's got the highest relative abundance, so the most particles were hitting the detector at that time when the 43 mass ions should have been coming out. We can also see from the spectrum the heaviest thing that comes out, which in this case has a mass of 72. And the heaviest species that comes out furthest to the right, we call this peak the molecular ion peak. And it gives the mass of the whole molecule that was put in at the start of the process. So you might look at this spectrum and think, well, if we've put a sample into the mass spectrometer that contains just one compound, then shouldn't we only get one peak out at the end? And that is what you'd expect, one peak weighing whatever the molecule weighed that you put in. However, quite often what you do get is a series of lighter peaks all along the spectrum. And this is something that happens particularly when you've used the electron impact method of ionisation at the start of the process. What happens is when these high energy electrons are coming in and smashing into the sample, not only are they able to knock an electron off, producing the 1+ ion, which is what you want, they can also fragment the molecule, so they can break a large molecule down into smaller fragments, and they are also ionised to a 1+ ion. They travel through the mass spec and they produce a peak. So it can be quite handy. It means that if you can identify what these peaks are, what they represent, what they could be in terms of how many carbons, hydrogens, oxygens, nitrogens are in it, you can start identifying fragments of molecules, and if you put them together to weigh the same as the molecular ion peak, then you can use your spectrum for some sort of structure determination to figure out not only what the molecular formula of your sample is, but also what its structure might be. However, the fragmentation, although it can be quite handy, it does give you a much more complicated spectrum to try and analyse, which is one of the reasons that we tend to use the electrospray ionisation instead. It's a lot less harsh on the sample and doesn't break it up into the fragments as often. Right, so one last exam question for you and then I'm done. This is something that you definitely should be able to do, so if you want to pause the video, have a go at it, see how you did when you resume the video. That would be really useful. Here we've got an element that's gone through mass spec, so you can have compounds, you can have elements. The compounds are the ones that tend to fragment if you use electron impact, but if you use an element, you start looking at isotopes and you identify the abundance of different isotopes in there and work out from that the relative atomic mass. And that's exactly what you're asked to do here. So you're given a mass spectrum of the isotopes of element X, and it asks you to have a little look at the spectrum, use the data from the diagram to calculate the relative atomic mass of X, and give you the answer to 1 decimal place. Always useful to read the whole question, 1 decimal place. So the way that you do this, you take the mass to charge ratio of the first peak and you take its relative abundance. You multiply these numbers together and then you do the same for each of the other peaks, and then you add the data for all of the peaks together. So the first peak, we have got a mass to charge ratio of 70, and that is multiplied by 3, which is its abundance, plus 72 is the next peak with an abundance of 4, plus 73 is the next peak with an abundance, let's turn that into multiply, times 1, plus the last peak is at 74, and you multiply that by 5, which is its abundance, and then what you do is you calculate that and then you divide through by all of the abundances added together. So we've got a 3, a 4, a 1 and a 5, which adds up to a total of 13. So plugging that into my calculator, I get 941 divided by 13, which is equal to 72.3 0.38, but obviously to 1 decimal place, which is what's asked you for, 72.4. Okay, and then, so that's the relative atomic mass of X. So on to the second part of the question, identify the ion responsible for the peak at 72. So we know the relative atomic mass of X is 72.4. Looking on the periodic table, the closest element to having a mass of 72.4 is germanium, which actually has a mass of 72.6. So I would have to assume that these relative abundances have been rounded to simplify the mass spectrum for us. So the element must be germanium. We know that it's an ion, and we know that it's travelled through with a 1+ charge, so it does need the 1+ charge. And we know it's an isotope of germanium because each of those peaks, these ones, are isotopes. So we want to specify which isotope it is, and it's given in the question. It's the 72 isotope. So if you're given a question like this, they do come up fairly often, or they have done in the past, make sure that you identify, if you're looking at a list of isotopes, make sure that you identify the mass of the ion, the 72, make sure that it is an ion and you've given it plus charge, and it's also asking you to have a little look on the periodic table and find out which specific element it is as well. So that's the full marks for that question. Right, just before we finish this tutorial, I just wanted to go back to something I said a little bit earlier when I was talking about the ionisation stage and how we aim to make 1+ ions. And I suggested that sometimes we can get +2 ions going through as well, and because they're positively charged, they'll still be accelerated by the electric field, they'll still travel through the drift zone, they'll still pick up an electron at the detector, and they'll be counted on the spectrum. So, on the spectrum, you've got the two axes, which you should already know everything about anyway. You've got the relative abundance, which shows how much of that particular species is present in the sample. So the 74 ion is the most abundant in this case. And we've got the mass to charge ratio. So MZ is mass to charge ratio along the bottom. So if your ions get a 1+ charge, like they should, like we hope they will, then you can assume, because it's mass divided by charge, if your charge is 1, then MZ is usually equal to just mass. So instead of considering 74 to be a mass to charge ratio, if we're assuming all of the charges are +1 anyway, then we can call this mass, and then that helps us to identify, for example, the peaks down here, or the relative atomic mass. Now sometimes they do trick you a little bit, and they ask you some questions about smaller peaks lower down the spectrum. So for example, on this spectrum, if we could see a little bit further to the left on this spectrum, down this way, you might see at a mass to charge ratio of 37, this tiny little peak over here. So they might actually put that on the whole mass spectrum. They might show you the all of the mass to charge ratios here. Obviously they've just gone from 69 to 75, and might show you a tiny peak at 37. So have a little think. I'm talking about this, the idea of most of the ions being +1 and hopefully being +1, what could the 37 peak be? It has been a question before, I've seen it asked a few times. Now if you're quite observant, you might notice that 37 is half of 74, and 74 is the most abundant ion. So if a 74 germanium plus ion gets a 1+ charge and travels through the mass spectrometer, it has a mass to charge ratio of 74 over 1. So that's 74 is the mass, 1 is the charge. So its mass to charge ratio can just be written as 74, and we get a peak at 74. However, if you end up with a germanium ion that weighs 74, that gets a 2+ charge, doesn't happen very often, but if it did, it would have a mass to charge ratio of 74, which is its mass, over 2, which is its charge, and that would give you a mass to charge ratio of 37, and it wouldn't happen very often, so it's not going to have a very high relative abundance, it would be a tiny, tiny peak, but that's what it's representing. So if you're seeing a tiny peak, much lighter than the rest of the peaks when you're looking at different isotopes, have a look, is that peak half the mass of something else? And if it is, it's that ion that's got a 2+ charge. Okay, so that brings us to the end of your first tutorial on mass spectrometry. It was just a recap, but it's a good place to start for your organic analysis topic, because we're going to look at mass spec in a little bit more detail as well as part of this topic. So now, if you would like to go on to the quiz for this tutorial, it's just 10 questions. I want you to whiz through those, complete them please before next lesson, and then I would like you to bring your notes from this tutorial to your lesson with you so that we can do some application and some questions.